the photo detectors.
Let's see. Yeah. Yeah, it works.
Right.
Can you see it?
Yeah, it looks wonderful. And it's very fast and yeah, looks good.
Yeah. Okay, so I wait until.
Yeah, I think we have, we still have a good amount of time, probably like 13 minutes or so. So I imagine people will trickle in, and they're also going to start the recording at some point. And
Okay.
yeah, so just take your time.
All right, thank you.
Is most of your time these days focused on the Juno experiment?
Yes, yes.
Oh, cool, cool. I'm not a neutrino physicist, but I am a theorist on black holes. And I was actually curious if I could ask you a selfish question on neutrinos.
Что абитуриент ждет от университета? Знания, опыт, образование или же студенческую жизнь? Я вам скажу, что КБТУ – это нечто большее. Это активная студенческая жизнь, новые знакомства, новые друзья. Опыт, навыки и знания, которые вы получите здесь, могут стать отличным стартом для вашей карьеры. Также в нашем университете вы можете встретить свою любовь. Теперь немного поговорим про учебную часть. КБТУ – это университет, который подготавливает и выпускает элиту Казахстана. Здесь вы можете наблюдать наши тренажеры, где студенты тренируются и обучаются. Станьте частью будущего вместе с нами.
Hello, my name is Donald Hoskins, and I'm a finance professor here at KBTU at the Business School. My background includes 25 years on Wall Street, and I bring that knowledge to the classroom to make finance come alive. Come to KBTU.
Hello, my name is Paul Davis, and I'm a professor at the Business School at KBTU. Students are able to major in management, This can lead to a range of exciting and interesting careers in the world of business and government.
I am also Said Najm. I am working as Center of Chemical Engineer at KB2 since 2015. It is a great pleasure to welcome to our center. Study at our center, provide students new knowledge, new technology. Our Center of Chemical Engineer has trained more than 500 chemical technologists. Our degrees lead graduates to successful lives and careers as scientists, specialists, and scholars. Our bachelor program is the best in Kazakhstan by independent Kazakhstan agency. We have international accreditation. Our programs licensed by international agency. I can say that KB2 is the #1 in Kazakhstan. It will be glad to see you in KB2.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you are. We have 2 hands, 2 eyes, 2 legs. We are simple human beings. And if we could do it, you can do it as well. So all the best, and hope to meet you all in the upcoming Festival of Nobel Laureates in Kazakhstan. Take good care of yourself and stay safe.
Welcome to the Central Asia Nobel Fest in 2021. This is John Mather, Senior Project Scientist for the James Webb Space Telescope, working at NASA in Greenbelt, Maryland, the United States. I'm interested in the whole history of the universe from the Big Bang to now, how life became possible on our own little planet circling an ordinary star, how we can protect our planet, and how far we can go. I hope you will find the Nobel Fest a fascinating adventure.
Hi, I'm David Spergel. I won the Breakthrough Prize in 2018, and I'm excited about speaking at the Central Asia Nobel Fest on my work and others on cosmology. Over the past 20 years, we've learned that atoms, the stuff that makes up us, makes up only 5% of the universe. So I'll be telling the story of how we probe the dark matter, the dark energy, and look back to the beginnings of the universe and learn how structure and galaxies and everything else emerges. Look forward to seeing you soon.
Hello, I'm Christopher Haken, 2018 Breakthrough Prize winner. I'm very excited about the upcoming Central Asia Nobel Fest lecture series. I hope you'll join us.
Nobel Fest.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you are. We have 2 hands, 2 eyes, 2 legs. We are simple human beings. And if we could do it, you can do it as well. So all the best, and hope to meet you all in the upcoming Festival of Nobel Laureates in Kazakhstan. Take good care of yourself and stay safe.
Welcome to the Central Asia Nobel Fest in 2021. This is John Mather, Senior Project Scientist for the James Webb Space Telescope, working at NASA in Greenbelt, Maryland, the United States. I'm interested in the whole history of the universe from the Big Bang to now, how life became possible on our own little planet circling an ordinary star, how we can protect our planet, and how far we can go. I hope you will find the Nobel Fest a fascinating adventure.
Hi, I'm David Spergel. I won the Breakthrough Prize in 2018, and I'm excited about speaking at the Central Asia Nobel Fest on my work and others on cosmology. Over the past 20 years, we've learned that atoms, the stuff that makes up us, makes up only 5% of the universe. So I'll be telling the story of how we probe the dark matter, the dark energy, and look back to the beginnings of the universe and learn how structure and galaxies and everything else emerges. Look forward to seeing you soon.
Hello, I'm Christopher Haken, 2018 Breakthrough Prize winner. I'm very excited about the upcoming Central Asia Nobel Fest lecture series. I hope you'll join us.
Nobel Fest.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you.
You easily lost flux.
Okay. So you can't look at the stars with a neutrino map. I see. Okay. Yeah. I mean, the Earth generates neutrinos itself, like the core, right?
Right.
And
that can be seen. That can be seen. Yes.
and what about the moon? Doesn't the moon?
Too small? I mean.
Oh, the moon is too small to see.
Right, the moon is smaller than the Earth, and we measure the neutrinos from the Earth at almost zero distance. I mean, from the moon, it's a long distance. You lose flux.
Okay.
Unless you put your detector on the moon, so of course.
Yeah. Oh, okay. Yeah, so new experiment idea. Okay, great.
Yes.
Let's talk to Elon Musk, see if we can get this done.
Indeed.
Okay. Well, they're going to tell me when we start, so I guess we just have to be patient. So
Okay.
I'll wait for them. Okay, great. Let me know when you're recording now. Okay. Welcome everybody. Thank you for joining us. It's wonderful to have you here with us. We have a very special speaker today, Yifang Wang, who is an eminent scientist and elementary particle physicist who has won numerous awards for his neutrino expertise. He's taken a leading role in detecting the unknown neutrino mixing angle and has won the breakthrough prize in fundamental physics. He is the director of the Institute of High Energy Physics at the Chinese Academy of Sciences in Beijing and has written over 300 scientific publications. It is a pleasure to have him here with us. And so please, Yifang Wang, thank you for joining.
Thanks. It's a great pleasure to be able to talk about our scientific work on elementary particle physics and also on the universe. So today I'm going to talk about the quest to the infinity. Indeed, particle physics is a continuation of the quest to the infinite small. We all know that from the history, people were studying molecules, which developed into chemistry. And we managed to know there are atoms, and that developed into atomic physics and also condensed matter physics, nuclei, the nuclear physics, and all the way to the quarks and leptons, which is the particle physics. So you can see that from the atom to quark, it goes from the size, almost 7 orders of magnitude. And these actually represent the evolution of science in the last several hundred years. So the quest to the structure of matter is actually a key driving force for the science development in the past a few hundred of years. And on the other hand, cosmology is infinitely large. So it is actually a continuation of the quest to the from the planet, solar systems, stars, galaxies, and all the way to the clusters and the universe. So we now understood from this study that the universe is originated from a Big Bang, and the process which governing this evolution is almost the same, following the same physics laws as we know on Earth. And the particle physics is indeed very much needed to understand the origin, the evolution, and the structure of the universe. So the infinite large and the infinitely small are all connected, because for particle physics, we order from quantum mechanics. If you want to know the inner structure, you have to break it. And the smaller the size, the higher energy is needed. And for the cosmology, and since we know it's coming from Big Bang, so which means it comes from a very high temperature. So high temperature and high energy, they all at the same, say, space-time point. You can see from the right curve, this is origin of the universe, starting from Big Bang and all the way expand to our today's universe. In your left curve, you can see that the infinite small and infinite large, they go around like a circle. The infinite large, infinite small, they all meet at the point where new physics laws, something like a grand unification theory, may tell us how this happened at this, say, starting point of the universe. So this is actually a very interesting connection between the infinite large and the infinite small. So for particle physics, we need tools to study the structure of the matter. In early days, we use microscopic microscope, which means we bombard the sample by photons, and you can see by your eye. And afterwards, you know that the photons, which has a wavelength, and you are not able to see anything which is smaller than the wavelength. So in order to see the inner structure, which is smaller than the wavelength of the light, of the visible light, you can use electron microscope, which has much smaller the wavelength, and you bombard the electrons, the samples by the electrons. So in this case, of course, electron microscope can see much smaller size of your sample. Similarly, if you want to go further deep into the structure of matter, you use accelerators. You bombard your particles by particles, and you see each other, and you know what is inside the particles. So accelerator is actually a key for the study of particle physics. And nowadays, we manage to build colliders to collide particles with particles, and we can effectively use all the energies to see the inner structure of a particle. Of course, there are other experiments on particle physics based on surface, underground, and even in space to study cosmic rays, study neutrinos, and also astrophysics. All these experiments were need detectors, or sometimes we call it spectrometers, to see the inside of the particles. So spectrometers are actually our eyes helping us to see the inner structure of matter or the particles. Of course, you have other tools to study the cosmology. So we all know that we use telescopes. Nowadays, we have optical telescopes, infrared telescopes, radio frequency telescope, and so on. And use all different type of detectors like X-rays, optical CCDs, gamma ray detectors, and also neutrino detectors, particle detectors, so on. And you may also place your telescope and or detectors in space to directly measure the cosmic rays, or the study the skies or the stars and so on. So in the right, you can see the development of tools from telescope of Galileo all the way up to space station operators, the AMS in the International Space Station. Of course, this study generate a huge impacts to our life. For example, we had a lot of high-tech outcomes coming from the construction of the apparatus for this kind of study. These including the microwave equipment, vacuum, mechanics, magnets, superconducting, cryogenics, and so on. And these all helped a lot the development of high tech and also implications to our life. In today's world, there are roughly 35,000 actuators in the world, and half of them are in hospitals for our health. And also in scientific research, we have been had the synchrotron light source and also spallation neutron source to help us to study the material science, condensed matter physics, geology, environmental science, chemistry, and so on. So these are the two examples. One is the Beijing high energy photon light source. Under construction, you can see the beautiful picture, which has a circumference of 1.3 kilometers. This is going to be the world's largest, world brightest synchrotron radiation source. In the right bottom, you see the just completed China spallation neutron source, which uses neutrons to study the structure of matter.
What's that? The facility with the largest synchrotron source?
This one is under construction, the Beijing high energy photon source.
In Beijing, okay.
In Beijing, yes. Under construction. So it's going to be completed by 2025. So the construction started in 2019. So of course, from point of science, after 70 years of study, we have a good understanding of the particle physics. Now we know that all the matters are made of quarks and leptons. So the best known lepton is the electron. So we all know that electron has been discovered more than 100 years ago, and we know it very well. And also we know there are heavier electrons, it's called the muons, and even heavier electrons called the taus. There are also corresponding neutrinos, electron neutrinos, muon neutrinos, tau neutrinos. Correspondingly, we also have 6 quarks, the UDCSTB. So all these 12 kind of particles are the building blocks of the matter, which then build up protons, neutrons, and then all the way up to our atoms, molecules, and our world. There are also particles which intermediate the interactions between these 12 elementary particles. So the first one is well-known photons, which mediate the electromagnetic interactions. There are also 2 other particles called the W and the Z, which mediate weak interactions. And the weak and the electromagnetic interaction can be combined into a complete one theory, which is called electroweak theory. So this is very much like Maxwell combined electron interactions and the magnetic interactions into electromagnetic interactions. So in the 70s and from 60s to 70s, scientists managed to unify the electromagnetic interactions and the weak interactions into one theory called electroweak. Now we have another theory which describes strong interactions called QCD, but we haven't yet managed to combine electroweak and the QCD into one even bigger theory of the unification. So this is actually the work left to the young generation to finish. Besides these particles, there's another very important particle called Higgs. Higgs is a particle which gives mass to all these elementary particles, including quarks, leptons, and mediator particles. The reason is that in order to have all these particles following a complete theory called the gauge theory, they have to have no mass. They have to have 0 mass in order to have the theory being, say, self-consistent. But in fact, we know that electron has mass. We know that W and Z has a mass. Quark has a mass. So in order to have the whole theory being consistent, we have to generate a so-called mass mechanism, now very often also called the Higgs mechanism, which gives mass to these particles in a way a little bit, say, arbitrary or by handwriting kind of interaction terms into the theory. So indeed, once this was originally invented, the people were doubt that this is really the case. And strange enough, after 30 years of study, the Higgs particles was discovered at CERN, which means that the Higgs mechanism is right. And the standard model is complete at this point. This is the year of 2012. So this is actually one of the greatest achievement in the history of science, not only for its scientific, say, achievements, but also for its technological achievements. And in this process, the World Wide Web, the WWW was invented, which almost changed everybody's life in nowadays. So we can see that science is not only bring to us the knowledge about the structure of the matter, the universe, but also bring to us a better life, including the technologies like the accelerators, the detectors, and also the information technologies like the World Wide Web. So we can see that science indeed is going to bring us a very important outcome, even though sometimes we are not able to predict beforehand. So standard model seems complete. We have all the particles, but indeed, if you think through, it is not a final theory. It is only effective theory at low energy, all the way up to only 1,000 proton mass, 1,000 GeV. So higher than that, we believe that there should be a new layer of physics beyond this kind of energy scale. There are many hints for such a understanding, for such a guess. First of all, we see that the mass of particles span over a scale difference factor of 10 to 13. So this is a huge difference of mass, and it's very hard to understand why for the same species like neutrinos and quarks, which are at the same, say, level of the structure of matter, the huge mass difference, 10 to 13. Secondly, the mass of Higgs is very small. It is actually a subtraction of two large numbers all the way up to 10 to the 34 number of digits. So this shows that you have to have some kind of accidental coincidence so that Higgs mass can be reduced all the way down to 125 GeV. So this is very unnatural. There should be a new physics behind it to have a cutoff so that you don't have to go all the way down to this kind of precision to have this cancellation. And also from the right plot, you can see that the measured top mass and the measured Higgs mass put the vacuum, our current vacuum, into a metastable region, which is also kind of strange. It's hard to imagine that our vacuum is not stable. And also in our standard model, there's no dark matter particles. We are not able to explain the matter-antimatter asymmetry in the universe. Neutrinos in the standard model is not well accommodated. We still don't know how to describe neutrinos in the standard model once it has a mass. And from experimental measurement, you can see that the current standard model made the coupling constant not matching at the higher energy point. While if you have supersymmetric models, you can see that their coupling constant can be unified at high energy. So you can see that a lot of, evidence or hints which point to a new physics beyond standard model. And many of these are related to the mass, or in other words, related to the Higgs. See, this is a mass issue, Higgs mass issues, dark matter is also mass issues, and this is also mass issues. So it looks like we still don't understand very well the mass, and the new physics may come out from the Higgs. So in the last 10, 15 years, people have been trying to understand what is the future of particle physics. And since 2012, we proposed that Higgs should be the target of the next high energy physics machine. And of course, people have been worked on the linear collider in the last 20, 30 years. But since Higgs is a low mass particle, a circular collider is indeed better in terms of luminosity than the linear collider, and the energy efficiency is also higher. So a circular electron-positron collider called the CPC was proposed, and this circular collider can be used for the first phase as a Higgs factory, and then in the second phase as a proton-proton collider, just like what had happened at CERN, the LEP and LHC. So this kind of scheme became a possible roadmap for the future of particle physics in China. And of course, afterwards, CERN adopted very similar scheme for the so-called FCC plan. So a little bit, say, precise, you look at what we can do at this kind of Higgs factory. If you look at deviation from the standard model, and this deviation is actually proportional to the mass scale squared. And if you look at the current search, we haven't seen any new physics at the level of 1 TeV. And the coupling constant precision right now measured at LHC is roughly 10%. And this 10% precision also corresponding to a mass scale, a new physics mass scale of roughly 1 TeV. So both direct and indirect measurement tells us that there's no yet new physics up to 1.1 TeV. At CPC, we are able to reach a precision at about 1%, which is order a factor of 10 improvement. And this tells you that we can really go all the way up to the 10 TeV kind of energy scale for the new physics. And this is actually very interesting because for 1 TeV kind of energy scale, you are going to require this kind of cutoff, the precision cancellation at level 10 to minus 2. And if you go to a 10 TeV, it's 10 to minus 4. So in fact, in nature, the accidental coincidence of cancellation at the level 10 to minus 2 is happening very often, but 10 to minus 4 is very hard to imagine and never seen before. So we believe that there's good reasoning or guess, good guess that new physics should happen at the level of 10 to of the 10 TeV. In addition, the Higgs particle is only spin zero elementary particles. So we don't know whether this is really elementary or it is similar to pion or Cooper pair in condensed matter. And this Higgs particle is also the only elementary particles with non-gauge interactions. So it is quite strange, and we believe that there is a lot of room for us to study, and there should be new physics behind it. So this is a design of the machine. The CPC is a double ring machine with the injector. The injector is going to accelerate the energy all the way up to 10 GeV, and then it go to the booster, and the booster can accelerate the energy from 10 GeV all the way up to 125 GeV, and then they accumulate enough current, and then they can collide. So this is the baseline design with 100 kilometers circumference, 30 megawatt the total power, and it certainly can be upgradable to 50 megawatt and also higher luminosity Z. So we came up since 2013 a plan of R&D, this including the electron gun, the positron source, superconducting RF cavities, klystrons, magnets, and so on. So I'm going to give you a little bit of examples of achievements we had since 2013. So these are some of the prototypes. You see a few of the magnets, electromagnet separators, vacuum pipes, and so on. So these are the prototypes we made in the last few years. Most of them satisfied our requirements. A few still need further study. Major progress is the RF cavities. These are the power source of the beam. So we really have to have a good quality, high performance RF cavities for a good accelerator. We have two types of RF cavities. One is 1.3 gigahertz 9-cell cavities for the booster, and another one is the 650 megahertz 2-cell cavities for the collider. And you can see that we managed to reach the desired specifications, and it shows that we can achieve the goal of the machine. So this shows that indeed the key technologies for the CPC has been taken in a good shape. We're also trying to build a new type of high efficiency klystrons. This can significantly improve the energy consumption. For such a large machine, remember we were talking about the 30 megawatt, which is actually almost a third of a nuclear reactor. So indeed, this is a huge power consumption. And if you are able to improve the efficiency from, say, 62% of current technology to 80% of the future technologies, we can certainly save a lot of energy. So this is the current effort. We managed to complete the first prototype, and we reached the designed efficiency of 62%. And now we are working on this new prototypes. The goal is 80% efficiency. By end of this year, it should be finished. Another R&D we are working on is plasma accelerator-based injectors. At CERN, there are a lot of existing accelerators being used as injectors, so there's no need to build new injectors. And for us in China, if we need to have this kind of collider, we had to build the injectors, which is also quite costly. A LINAC of 10 GeV or 20 GeV is quite expensive. So we came up with the idea that we use new technologies like plasma acceleration technologies to increase energy by a factor of 2 or 3. So instead of, say, 10 GeV into the booster, we can use one stage of plasma accelerator to go to 45 GeV. So this can significantly reduce the requirement to the booster and save the cost of the construction of a booster, but also to develop the plasma accelerated technologies. We all know that plasma accelerated technology has not yet been really used in a real, say, case. So here, by using traditional accelerator technologies before the plasma accelerator, and also after the plasma accelerator, but just use the plasma accelerator as an intermediate stage, we can avoid shortcomings of the plasma accelerator and use its advantages. By the design and simulation, we understood that this is feasible, and R&D is actually going on right now. Another technology we are actually working on is the high TC superconducting cables. This is actually not for the CPC, but for the future proton machines. The future proton machines actually depend very much on the magnet. You need a very high field strength of the magnet. The current technology like Moderator is difficult, but can only all the way up to 16 Tesla. So if you want to go to all the way up to higher than 16 Tesla, you need new technologies. On the other hand, you need to find a way to reduce the cost and materials of the cable and also the magnet itself is the main, cost factor of the future proton machine. So we came up with the idea that we should use completely new technologies for the high TC superconducting cable. Ion-based high TC is actually a good choice because it is different from, say, copper-based high TC cables. Iron-based is a metal, while copper-based is a ceramic. So you can easily imagine that a metal cable is much easier, much better than a ceramic one. So easy for process, isotropic, and in principle, very cheap. So we had actually a very good start in Chinese chemical sciences. The record of the highest TC material was actually set by Institute of Physics of Chinese Chemical Sciences. And also were the first 100-meter long ion-based superconducting cables were made by the Institute of Electric Engineering. So we're actually working with them to build the world's first ion-based superconducting magnet. Indeed, you can see from this right curve, the cable and also performance of the cable. And also we had the first ion-based superconducting coil running in the background field, and it is actually demonstrated that ion-based magnet can be worked in a more than 20 Tesla field. So this is a very promising progress, and we hope that we are able to improve further the current density by another factor 10 and reduce the cost by also another factor 10. So totally a factor 100 improvement, then this kind of cable is going to be realistically usable. Anyway, CPC is going to be a China-initiated large international science project. We hope that we can get 1/3 of the international contributions, and we're actually seriously discussing with the international high energy physics community. An international advisory committee board has been established, MOU signed, and international workshops have been organized. Except the last one in Marseille, because of the pandemic, has been postponed to this year, to mid of this year, and it may need to be delayed further. Of course, the idea of CPC is not just coming out from scratch. We had 30 years of experience of electron-positron colliders. So this is the Beijing electron-positron collider running at the Taochang factory kind of energy range. You can see from the top right curve, BEPC was initially proposed and built in 80s. And then in the beginning of this century, there was an upgrade called the BPC2, and the luminosity were always the highest in the world. So these two machines actually lay down the foundation of our experience and technologies for the electron-positron collider. And these BPC and also the experiment called the BESS-3 had a lot of scientific outcomes. Currently, this international collaboration has roughly 500 members from 60 institutions of 13 countries. Some of the major discoveries, scientific discoveries, were the observation, the ZC3900, also the neutral ZC3900, and also ZC4025, 4020, and other exotic light hadrons like X1835, X1870, and so on. So totally more than indeed 300 papers published, and we are going to continue to operate for another roughly 10 years. So in the end, let's look at the particle physics as a global as a global picture. So for science, we have a standard model in the middle, and we try to study the Higgs, study the CP, violation neutrinos, hadron physics, and the precision test. You can see that there are many experiments around that, like AMS for the antimatter, neutrinos, Diabase, Juno, etc., and the dark matter experiments in underground and also in space. There are axion searches. There are hadron physics, rare decays, the precision measurement of G-2. This is very famous now, and also LHC experiments, Atlas and CMS, and the future IRC, FCC, CPC, and so on. So this is a global picture of particle physics. And China is actually having a quite complete particle physics program around almost all the disciplines or different directions. For the X-ray-based experiments, we have now BESS-3. We are also members of HCB, BEL2, PANDA, and so on. And in the future, we hope to be either part of IRC, FCC, or the CPC. In Energy Frontier, we are members of CMS, Atlas. In neutrino physics, we have Diabase, Juno in the future, and there are also dark matter search experiments. We have cosmic ray experiments like Argo, AS Gamma, and currently LASO is operation. We also have a cosmic microwave background experiment called ALI-CMB. In space, we are a member of AMS, and also we have few satellites for X-rays and also dark matter searches. And in the future, we have a two experiment and the planning. So red one with question mark are experiments not yet approved, and the white one are the experiment now under construction. So the neutrino physics in China started from the Diabase experiment, which trying to measure neutrino oscillation parameters called the θ13. Before that, θ12 and θ23 had been measured by Snow and Super Kamiokande experiment, and they discovered the neutrino oscillation. And of course, once you know these two parameters, you have a very natural question: what is the θ13? And there are theories which predict that θ13 could be even 0. So we designed our experiment to have 3 locations, 2 so-called the near side and the one far side. They have they have a distance of something like 1.6 kilometers. And in each experiment hole, we have either 2 detect modules or 4 detect modules. By doing this, we can reduce the statistic and the systematic errors quite significantly, and also give us quite bit of redundancy. If any one of the module failed, the experiment can still move forward. Fortunately, we see that the neutrinos from the reactor disappeared on the way from the reactor to our detector. And this disappearance had a probability of roughly 6%. And this can be translated into the oscillation amplitude of 0.092 plus minus 0.16 plus minus 0.05. So this is actually 5.2 sigma significance for non-zero theta 1,3. And this is, of course, the first measurement to determine the theta 1,3. And of course, very excitement in the world. Theta 1,3 is one of 28 free parameters of the standard model, and also one of the 6 oscillation parameters. Once we know the theta 1,3, the oscillation pattern is completed. The precision of the sine squared 2 theta 1,3 measurement had been improved from 20% in the year of 2012 all the way to 3.4 right now. And we are going to continue to analyze data. We believe that the precision can be improved to slightly less than 3%, say 2.7. And indeed, combined with T2K nova, the leptonic CP phase is now estimated to be roughly minus 90 degree at 2 sigma level, and you can see from the right. And because of the large enough theta 1,3, new experiment could start. This includes Juno in China, Dune at BNF in the US, and also HyperK in Japan. Diabase is a large international collaboration. We have something like 41 institutions, 200 collaborators, mostly from China and the United States. The next step is the Juno experiment. You can see that Diabase is located here, which can measure neutrino oscillation amplitude theta 1,3 and at this oscillation maximum. If we put our detector at the oscillation maximum of theta 1,2, we can actually measure the neutrino mass hierarchy, the datum 3,2, the sign of datum 3,2. Indeed, we managed to find an optimal place in China, in Kaiping County. This place, we find a small mountain, and under the mountain we can build a laboratory, which has the equal distance to 2 reactor complex. One is called the Taishan, and another one called the Yangjiang. So the distance, the baseline is 53 kilometers, exactly the location of the oscillation maxima. With such a detector in a distance to the reactor of roughly 53 kilometers, we can determine the neutrino mass hierarchy at 4 sigma level in 6 years. And on top of it, it is independent of the CP phase. This is different from the other experiment like Dune and the HyperK. They depend very much on the CP phase value. And we can also measure neutrino oscillation parameters to precision better than 1%. And you can imagine that currently with many of the B factories, C factories, and the 5 factories, we only manage to measure CKM match element at a level of 1% or slightly bigger than 1%. And with one experiment like Juno, we can measure all these parameters to less than 1%, which is very important to test the unitarity of the oscillation matrix. You can also study the supernova, the geoneutrinos, solar neutrinos, proton decays, and so on. So I'm going to skip this. The detector is a 20 kiloton large liquid scintillator detector, which is almost factor 20 larger than the ChemLand detector, factor 40 larger than the Boltzino detector. The light yield has to be factor 2 larger than Boltzino, factor 5 larger than the ChemLand. So this is a technologically very difficult detector. We have to build a very large underground cavern with a diameter of 50 meters, with a height of 70 meters. The aquatic tank has a diameter of 35 meters, which is almost 12 layers of 12 stories of building. So you can imagine this is a huge construction. And then we need to have a very transparent liquid scintillator, 25 meters long of attenuation length. And also we need to have very high efficiency 20-inch photo tubes. When we designed the experiment, we have only available Super K photo tube, which is only half of the detection efficiency we need. So this is also a challenge for us during the design and the development of the Juno detector. So these are some of the examples. For example, the acrylic tank, you see our prototypes of 9 panels of acrylic. We try to see how we are going to bond these panels into one big piece, make sure that they are safe and they are quick enough and they are high quality and so on. Then we need to have a standard structure to hold the acrylic tank, and we have to worry about the precision, worry about the thermal expansion, worry about earthquake, and so on. And then we have this 20 kiloton liquid scintillator. We have to worry about the purification, both for the transparency and for the radio purity. For the phototube, since 2009, we started to develop a new type of 20-inch photomultipliers. We call the microchannel based photomultipliers with efficiency, say, more than 35%. After years of effort, we managed to reach roughly 30% of detection efficiency. And in the meantime, Hamamatsu also improved their detection efficiency to the level of roughly 30%. So this is the contract, and indeed, all the photo tubes have been delivered, and NNVC managed to reach 30%, and Hamamatsu is 28%. So indeed, we got all the photo tubes, or it's written here. So Hamamatsu 28%, NVT 30%. So we managed to got all the photo tube delivered and tested. Finally, we need to have underground civil construction. So we need to go all the way down to a slope of 40% kind of slope tunnel to the underground laboratory. And then we need a vertical shaft to get access to the underground laboratory so that we have something like 700 meters of overburden for our detector. And the construction is now almost finished. We are working on the water pool. This shows you a picture. So the Juno is a large international collaboration. We have right now more than 600 members, 77 institutions and 17 countries. Finally, let's talk about the future of neutrinos. So in 10 years from now, we believe that oscillation will be completely understood. So the mass hierarchy and the CP phase will be determined by Juno, by Dune, and also by Hyper K. Then the next breakthrough should be the zero neutrinoless double beta decays. The reason is the following. From cosmology, we know that the neutrino mass should be less than 1 electron eV. From oscillation, we know that the lightest neutrino should have a mass say roughly 1 millieV. And from beta decays, we can probe the neutrino mass to the level of 0.2 eV. And this is effective neutrino mass from beta decays is actually expression of a summation of mass eigenstate of neutrinos into this flavored eigenstate of beta decays. So double beta decays has a slightly different expression, but still it's a function of the mass eigenstate. So if you look at existing experiments and also their target mass, you can see that in the next few years, say 10, 20 years, the effective neutrino double beta decay mass is should be able to reach a level of 10 millieV or a few millieV. So Juno in the end has the capability to upgrade into a double beta decay experiment after the mass hierarchy determination is finished. So we can load the liquid scintillator detector with xenon 136 or tellurium 130. And then in this case, we are going to have a target mass of say 50 tons, which is almost the order of magnitude more than anybody else in the world, and we can get a very high sensitivity to the neutrino less double beta decay, say effective mass, and we are able to probe the neutrino mass. Anyway, that's the end. Our understanding of the matter in the universe has had great achievements, incredible success in the past, more to come in the future. And actually we are catching up thanks to the economic growth. Diabase and the battery had great success, and we hope that we have bright future for Juno and the CPC. So welcome to join us. Thank you.
Thank you so much. It's a really nice talk, and it's good to see so many experiments and so much progress towards this. It's clear that the funding is there and the political will is there. I'd like to give a moment to the audience to ask questions. So let's take a few questions. You feel free to show your video and unmute yourself and ask whatever comes to mind.
I have one question. In the future, if I want to work with Juno, in Juno, what I need to do?
Send me an email. Well, I mean, it's a little bit to say naive, but indeed, we have a lot of collaborators, institutions, and if you believe you are interested, if you're you are interested in person, you can try to say join one of the Juno collaborating institutions as say professor, postdoc, visitor, and whatever. And if you want to join Juno as an institution, you should apply to our institutional board, express your interest, your capabilities, and also your possible contributions. And we will evaluate, and then mostly we accept applications. I mean, up to now, we never reject any applications yet.
Okay, thank you so much.
So send me email. So I guess your colleagues have my email. So send me email. We can start the process and tell me what you need. Yeah.
Hello. May I ask?
Yes.
So I want thanks for interesting presentation. So my question is the following. So for construction of all matter in the universe, the lightest quarks are enough. Yes, you have up and down. It is the first generation. So, but we have second and third generation of particles. Yes. So
Yes.
how we can explain, because for now we don't need them. So in the early universe, probably they were very important. So how why we had this three generation of particles, lightest and then more heavier and the heaviest. So what you can say about this?
This is a very, very interesting question. I think it's a very good question. In 60s, when we know we have electrons, we have protons, neutrons, we have UD quarks, we thought we solved all the problems and everything needed are there. But then suddenly with higher energy accelerators, we had the second generation, third generations, and made our life much more complicated and difficult. I think this is just nature, and we have no explanation why you need three. Of course, we know we have only three. We don't have four. Why three? Why not two? And why not one? I have no idea.
Okay, thank you very much. Good. Okay.
Hello, may I ask you some question? As we know that these lectures are designed to motivate students and other peoples, so can you share with us about your experience and some difficulties which you meet while working at this project? Because the workflow is so interesting in organization or presentation your project to other people. Thank you.
For a large project like this, particle physics, typically, of course, you are going to face a large number of problems. I mean, from say funding, organization, people, technology, science, etc. I mean, I cannot count them, and it's almost infinite. I mean, but on the other hand, if you really believe what you are doing is right, and if you are able to use the science to motivate your people, and we can all work together to overcome any kind of problems. So I think in the process, I think the only way to support us to move forward to overcome the problems is the science, and we all have the same goals. Whenever we have difficulties, we have different, say, opinions and so on. We discuss, we talk, and we finally, since we have same, say, belief, the same goal, so we should all be able to find a solution. And this is also exactly the same reasoning to talk to the funding agencies.
Okay, thank you. I have another question about your experience maybe and your future, and what hopes do you have for future students which in school now?
Yeah, I think for students, I think I have three hopes. First of all, they really believe in science. They are devoted to science. And secondly, of course, you have once you have the motivation, you are actually how to say, you work for yourself, and you are you do everything for yourself. So you are able to self control and self-motivated to work on any of the projects. So you don't have to, you should not wait for somebody else to tell you to do something or how to do things. You really have to self-motivate it and do things by yourself and overcome the problems. And of course, thirdly, you have to have, basic training. You have to know basic things. And once you have these three, I think you should be able to be a good scientist, no problem.
Thank you for your answers.
I have a question. When you start such a big project like yours, what is the start? You just call the subject of the research and you're starting to look for scientists and combine in one team, or you already know each other and you decided to work on some certain subject and then create collaboration?
Yeah, usually we have a core team. This core team are people whom we know each other for a long time, and we have, say, enough needed expertise to come up with a conceptual idea for the project. Once we believe this works, and then of course we go out to talk to our friends, to talk to different people in different countries to attract their interest. And then after we have, say, reasonably large enough group, then we try to share the responsibilities, distribute the tasks, and come up with, say, a real design and the proposals. And then we go to respective countries to ask for funding for their responsibilities.
And how long does it normally take from the time when the idea came up and for the moment when it really starts?
Sometimes more than 10 years, sometimes a few years. So for example, diabate took us 4 years, starting from the idea all the way up to the start of the construction. CEPC already took us 9 years. We haven't reached to the stage of the construction. So we haven't got the approval, and we don't even know when or how we are going to be approved. So it's still, I believe it is going to take us still another 4 or 5 years.
Thank you.
These are really good questions. I think we also have a question in the chat by Nurbek Achalov. He says, what are the requirements for cooperation within new projects for Kazakh research institutions? I believe there was an MOU signed, a memorandum of understanding that you mentioned in your talk. Perhaps you might elaborate on the requirements for official collaboration with Kazakh institutes.
Yeah, so usually we have kind of MOU agreement. People just talk, and we come up with a signed MOU with respective funding agencies, and so it's not that difficult, and it's also how to say, every collaboration is different. So there's no, say, one formula for every experiment. Since we are working on the same goal, we all believe this is a great, say, project. Then of course we enthusiastically work together to come up with some kind of formalism, but not very complicated, not very difficult.
Maybe I can ask a question. I'm curious about, suppose there was a fourth generation of neutrinos and you learned the mass of one of them. Would it really mess everything up to try to find all four? Or is knowing the mass of one neutrino enough to find three of them only if there's three generations? Do you know?
Yeah, because at this moment, from the standard model, we know that there are only three generations. If you had the fourth generation, the mass of neutrino has to be more than 45 GeV. This is determined by the width of the Z particle, the Z boson. So it's hard to imagine that the 3 neutrinos with a total mass less than 1 eV and the force is more than 45 GeV. So this is hard to imagine. So we believe it doesn't exist.
Yeah, stranger things have happened, but it looks like there's a good reason to believe there's no 4th generation of neutrinos. Yeah, interesting. Wow.
Force Dirac neutron, to be precise.
Okay, Dirac.
Force Dirac neutrinos. Now, of course, people were arguing that you may have the star neutrinos, the right-handed neutrinos, which is still a question. We don't know. And there are also a lot of experiments trying to look for this kind of star neutrinos, because star neutrinos does not interact directly with matter. So you had to go through the mixing of a star neutrino with normal neutrinos, and then you see it. It's quite complicated. So a lot of people also believe that they shouldn't be there.
That's fascinating.
I saw in chat there's another question. The student, how could collaborate in the future? But now he's a student. I have to study. And what do I need? Well, I think you need to study particle physics, field theory, experimental, say, techniques, detectors, and so on. So, of course, if you didn't, it's not a problem. And if you wish, you can join us as a student. Once you come to us as a graduate student, you will be able to get the chance to learn these courses.
Great. Let's give one more moment for any further questions. Okay. It's fantastic to have you here. I really do hope that maybe you can show up to Astana in person one day soon and see this beautiful city and the country. It was great having you give a talk, and maybe we'll have you again participate in Nobel Fest 3.
Thank you very much. I really hope that I can visit your country and visit your people, and that will be my real hope. Yes.
All right. Okay. Thank you so much, everybody, and appreciate your attention and time. See you later.
See you. Thank you. Bye bye.
Bye bye.
Dear students and colleagues, my name is Aaron Chikanover, and I am an Israeli physician and biologist working at the Faculty of Medicine of the Technion, which is Israel Institute of Technology in Haifa, Israel. I happen also to be a laureate of the 2004 Nobel Prize in Chemistry for discovering the ubiquitin-mediated proteolytic system. I intend to participate and to give a talk at the Central Asia Nobel Festival series of lectures, and I invite you all to participate, to inspire us and to be inspired. But mostly, I want you to learn from this participation one lesson. People like us who made important discoveries are human beings exactly like you are. We have 2 hands, 2 eyes, 2 legs. We are simple human beings. And if we could do it, you can do it as well. So all the best, and hope to meet you all in the upcoming Festival of Nobel Laureates in Kazakhstan. Take good care of yourself and stay safe.
Welcome to the Central Asia Nobel Fest in 2021. This is John Mather, Senior Project Scientist for the James Webb Space Telescope, working at NASA in Greenbelt, Maryland, the United States. I'm interested in the whole history of the universe from the Big Bang to now, how life became possible on our own little planet circling an ordinary star, how we can protect our planet, and how far we can go. I hope you will find the Nobel Fest a fascinating adventure.
Hi, I'm David Spergel. I won the Breakthrough Prize in 2018, and I'm excited about speaking at the Central Asia Nobel Fest on my work and others on cosmology. Over the past 20 years, we've learned that atoms, the stuff that makes up us, makes up only 5% of the universe. So I'll be telling the story of how we probe the dark matter, the dark energy, and look back to the beginnings of the universe and learn how structure and galaxies and everything else emerges. Look forward to seeing you soon.
Hello, I'm Christopher Haken, 2018 Breakthrough Prize winner. I'm very excited about the upcoming Central Asia Nobel Fest lecture series. I hope you'll join us.